Hi, my name is Lilia. I'm from Synopsys, and I'm very excited to show you our demo which runs accelerated SLAM stack and object detection CNN graph simultaneously on ARC EV processor. Simultaneous localization and mapping, or SLAM, is a technology that allows you to build and update a map of an unknown environment while at the same time keeping track of agents' location within it. It is a key component in a variety of systems, like autonomous vehicles, robotics, augmented and virtual reality. Combining SLAM technology with a deep neural network engine, or DNN, gives a more intelligent system, which is able, for example, to identify objects in the environment and make decisions based on what the algorithm sees. For this demo, Synopsys has collaborated with our partner, Kudan, and accelerated their KudanSLAM product using ARC EV processor. Let's take a look at the demo itself. The demo has two main components. The first component is the x86 PC, which is a host. The second component, the accelerator, is the hub's S52 development platform. That is an FPGA-based system configured with ARC EV processor. The host is responsible for running the non-accelerated part of the SLAM stack and the host application. The host application controls the communication with EV, feeds the SLAM algorithm with the data from the accelerator, and visualizes the SLAM map. In our demo, we used x86 host only for the convenience of implementation and 3D map visualization. In real application, the PC will be replaced with an embedded host, often with Linux-like operating system, so the rest of the SLAM stack will be executed on the embedded host. The accelerator contains the vision engine, or VPU, and the DNN engine. The DNN engine runs the 3D object detection graph. The VPU is responsible for the SLAM acceleration. The acceleration strategy that we used allowed us to achieve up to 40% increase of the SLAM algorithm's performance. The demo is running on a 60 MHz FPGA, therefore the performance isn't real time. So let's take a look at the results. The first use case that I'm going to show is an automotive video. The input for the demo, on the left, is a front view driving video, captured from one camera, so SLAM is working in a monocular mode. The video is processed by the SLAM stack, and the generated map is rendered on the right. The CNN graph is running at the same time. It jointly detects objects on the input image and predicts their 3D coordinates. Then these 3D coordinates are translated to the SLAM map space. The host application is responsible for recognizing the previously detected objects and draw them until they are truly lost, even if CNN misses the detection for a few frames. The map is interactive. The user can drag and zoom it in and out to see some interesting parts, as for example loop closure process. Here you can see that the camera is moving towards a place where it has already been. It starts turning, and the map now is wrong, because the error has accumulated while the map was building. A little bit later, SLAM will recognize the place in previously built portion of the map and recalculate the camera's position. Once the camera's position is fixed, SLAM starts correcting the wrong portion of the map and closes the loop. The loop is closed and the map is corrected. The resulting map is very accurate and is generated based entirely on front view video capture from the car. Let me show you two more SLAM applications which don't use CNN but highlight that SLAM can work in many different environments of different sizes. For example, SLAM can build a map of the room. The visualization in this case is truly 3D, so you can not only drag and zoom but also rotate the map. In this video you can see very clearly the room's rectangular form and the outlines of blinds on the windows. This video shows even smaller environment, the objects lying on a table. But still, SLAM works very well and you can see very clearly the outlines of the objects, like t-shirt, scarf, hat, album cover. How did we achieve these amazing results? Our partner Kudan helped us to profile their SLAM stack when it was running exclusively on an embedded host. Their performance report helped us to identify the functions which were the best candidates for the acceleration by the EV processor. Offloading a part of the SLAM algorithm from the host processor to EV's VPU allowed us to achieve up to 40% performance gain. What exactly has been accelerated? KudanSLAM algorithm has two main parts: front-end, which is responsible for the feature extraction and matching, and back-end, which is responsible for map correction. we've accelerated a part of feature extraction pipeline. SLAM acceleration is not the only thing done by the EV processor in this demo. VPU is working simultaneously with the DNN engine, but on independent tasks. The VPU processes the image data which is needed for SLAM processing, and the DNN engine runs the 3D object detection CNN graph. I hope you enjoyed watching our demo, which showed KudanSLAM stack acceleration combined with object detection CNN graph running simultaneously on ARC EV processor. If you'd like to learn more about ARC EV processor, please visit synopsys.com/ev. Thank you.